Hi guys, this is lesson 5-6. It's the very last lesson of chapter 5. We're going to talk about how to graph these linear inequalities. And there's a lot of similarities to graphing equalities, but we're going to be coloring in entire regions rather than just leaving a plain line. There's a couple of things to consider. We are going to have a boundary, so you can see in this graph right here, there's a boundary, and that boundary line is going to either be a solid line or a dotted line. It's going to be a solid line if we have an or equals situation, and it's going to be a dotted line if we have just a less than or greater than. That's what they're talking about here when they say a closed half plane or an open half plane. They're just talking about whether or not we have a dotted line or a solid line. So we are going to be graphing a boundary. We are going to be using a test point to see which side of the boundary we're going to color in, and then we're going to be doing the coloring. So let's look at an example. So here's the book example, and you could look at this in detail if you wanted, so I'm going to actually work a different one. But just in brief, we're graphing 3x minus y is less than 2. And what they've done here is they've rearranged the equation so that it's in our sort of y equals mx plus b form, because they're going to use the y-intercept and the slope to graph the boundary line. There are other ways to do this. We could substitute in zeros to get points, but for now, we'll just go ahead and rearrange these to keep it simple. Once we've rearranged it into this y is greater than 3x minus 2, then we actually pretend for just a few minutes that that greater than is an equal sign, because we want to be able to graph this line right there. And we know how to graph y equals 3x minus 2. What we do is we look at the y-intercept, which is negative 2, and then we look at the slope. 3 means rise 3, run 1. So we go up 3 and then over 1, and then we connect the dots with a line. In this case, we're going to use a dotted line because this is a greater than, not a greater than or equal to. All right, once we have our line in place, then we're going to test a point. And in this case, they're going to select 0 and 0 as a test point because it makes the math easy. You could pick 5,000 and 6,000. It doesn't really matter where you want your test point. It's just that you might pick 0 and 0 just because it's kind of easier math. We put that test point in. Let me get rid of my mark there. We put that test point in the equation. There's the 0 for x and the 0 for y. And we end up with 3 times 0 minus 0, which just equals 0, is less than 2. And 0 is indeed less than 2, and so that's a true statement. So we go to the point 0 and 0, which happens to be right there at the origin, this point right here, and we know that that point, since this is a true statement, that point has to be in the area that we're going to color. So we go ahead and color in this region right here, not the white region. We're going to color right over our test point. Now, if it had been false, then we would not want to color over that point. We'd want to color on the other side. All right, let's do our own problem here. The first one right here, let's just do y equals, y is greater than 1/2 x plus 3. It's already in this form, y equals mx plus b. That's great. So we're just going to pretend. Remember, we're pretending, but then we're going to get this greater than sign in there. We're going to pretend that this is y is equal to 1/2 x plus 3. I'm hoping that looks familiar to you because we've been graphing things now for a while. All right, I need a graph. This will be our x-axis and our y-axis, And we're going to start at the y-intercept, which is 3. So 1, 2, 3. This is where our y-intercept is. And then my slope is rise over run, 1 over 2. So I am going to, from the place where I put my y-intercept, I'm going to rise 1, that would be to there, and then I'm going to run 2, 1, 2, and then I'll put a dot. I can do that a couple times if I want to. Rise 1, run 2, rise 1, run 2, if I wanted a little more to connect. All right, now we need to decide whether we want a dashed line or a solid line. So we need to go back here and look. This was actually not an equals, it was a greater than. So since y is actually greater than 1/2 x plus 3, it is not or equal to, so we need a dotted line this time. Dot, dot, dot. This is my boundary line. Make it nice and big. All right, now I need to know whether I'm going to color above the boundary line or below. I'm going to guess that it's probably above because y is greater than 1/2 x plus 3. However, let's check it. I think I'm going to choose this as a test point, 0 and 0. So let's plug 0 and 0 into the equation and see if it's true. Y is going to be 0, is greater than 1/2, x is going to be 0, and plus 3. And if I solve that, I get 0 is greater than 1/2 times 0 is 0, and 0 plus 3 is 3. Is 0 greater than 3? No, it is not. So where my test point is, I am not going to color. I'm going to color the other side. So let's, I don't know what color we want to do here. Doesn't really matter, but we're going to be coloring above the dotted line. All right, so that'll be where all of the numbers are that happen to make that a true statement, y equals 1/2 x plus 3. If I were to pick a number that was up here on the graph, maybe, let's see, 1, 2, 3, 4, 5. Let's say 2, and 1, 2, 3, 4, 5, 6. 2 and 6 would definitely be in there. So I could test that out. I would have 6 is greater than 1/2 times 2, that was my x, plus 3. And I would have 6 is greater than 1/2 times 2, happens to be 1. And plus 3 is 4, and yes, 6 is greater than 4. So I know that all of my solutions live up here that make this a true statement. All right, let's go on. This time we're going to graph with an or equals. Okay, so here's an example. They have graphed x plus 5y is less than or equal to 10. They rearranged it and made it in y equals mx plus b order. And then they pretended it was an equals so that they could get their boundary. They looked at the y-intercept, which was 2, right there. And then they looked at the slope, which was -1/5. That is down 1, run 5. So they went down 1 and they ran 5. 1, 2, 3, 4, 5. And then they connected the dots with a solid line because it's or equal to. Less than or equal to. All right, and then they used a test point. This time they decided to use 3 and 3. Whatever floats your boat, you can test any point you want to. 3 and 3 happens to be 1, 2, 3, 1, 2, 3. It's right there, okay? They could have chosen 0 and 0. That would be fine. They chose 3 and 3, and when they plugged 3 and 3 into the equation, 18 was not less than or equal to 10, okay? If they had plugged in 0 and 0, they would have got 0 is less than, let's see. 0 and 0. They would have gotten 0 is less than or equal to 10, which is a true statement. Okay, their statement was false, so we do not want to color where their 3 and 3 point is. But if we had put 0 and 0, we would have gotten a true statement, and then we would have colored. See, the blue area definitely covers 0 and 0. So that's fine. But their point did not work, so they did not color above the line. And yeah, let's go down here and do x minus y is less than or equal to 3. We want to get our y by itself, so let's subtract x. And we have negative x, yuck, is less than or equal to negative x plus 3. So I put the negative x first. I did that because I wanted in y equals mx plus b form. All right, I don't like the negative y, so I'm going to have to divide or multiply everything by negative 1. Look what that does. Okay, flip the sign. Then negative divided by negative gives me a positive. Great. And I'm just going to change every sign on the other side. So x became positive, 3 became negative, and now I have y is greater than or equal to x minus 3. I'm going to pretend just for a moment that this is y equals x minus 3, so I can get my boundary line. I'm going to start at the y-intercept, which is negative 3, right there, and my slope is 1, so I'm going to rise 1, run 1. Rise 1, run 1. Rise 1, run 1. Rise 1, run 1. I want a solid boundary line because when I go back to look at what this actually is, not equals, but it is greater than or equal to. So I want to use a solid line because I have this or equal to. All right, where do I color? Top or bottom? Well, I'm guessing it's going to be above because it says y is greater than. But if I want to test that, I'm going to go back to this 0 and 0 because it's such an easy one to test. Let's plug those numbers in. 0 is greater than or equal to 0 minus 3, or 0 is greater than or equal to negative 3. Yes, it is. So I'm going to color over the 0 and 0 point, because this area has all of the solutions that make my equation, my inequality, true. Okay? Now, what if I want to solve an equation? So I can solve this equation because it doesn't have a y and an x, it just has an x, so I can solve it. And in this case, I can actually, they say you're solving it, they say you're graphing it to solve it. It's kind of both at the same time. So notice what they do is they pretend that it is equals. They actually go ahead and subtract 5 from both sides. They divide by 3, and they get x equals 3. And they're going to use a dashed line because it is less than. It's not or equal to. So notice how they use the dashed line. And then they use a test point 0 and 0. They find out that it is indeed true that that works. If we plug it in, what we end up with is 5 is less than 14. If we plug in the 0 for x. And so we're going to color to the left of our straight up and down line, and we have a nice solution set there. And we can see that since the shaded area is to the left of the dashed line, that we know that all of our solutions happen to be less than 3, and so we have a less than 3. So let's see if we can do this. We have 4x minus 3 is, let's just pretend it's equals because we're kind of using this to solve. And we could just go ahead and solve it. I don't know exactly why you would do this. I think you would normally, to be honest, just solve it the way we've been solving it and then graph it if you need to graph it. But we're going to do it exactly the way they want us to. So let's add 3 to both sides. We get 4x is equal to 20. Nice. We divide by 4. And we get x is equal to 5. We had an or equal to in this case, so we're going to use a solid line. So 5 is 1, 2, 3, 4, 5. So I'm going to make a straight up and down line right there. And I need to know where to color. So let's pick a test point. I still like 0 and 0. Don't get so hung up on it that you think you have to use 0 and 0, because sometimes 0 and 0 is on a line and it's not convenient, but so many times it is that we're just going to use it. If I plug that in, I'm going to have 4 times 0 minus 3 is less than or equal to 17. That was my original equation up there. 4 times 0 is 0, so I get negative 3 is greater than or equal to 17. No, I don't think so. So we are not going to color where our test point is. We are going to color on the right. So coloring over here like this. And now I know that all of my solutions happen to be greater than x. So I'm going to say that x is greater than 5 or equal to, because I use that solid line. So there we are. And that's how you do it. Okay, let's do some check your understanding problems here. So if we are asked to graph each inequality, we will do something like y is greater than x plus 3. We will graph y-intercept and slope. So that one's not too bad. Y-intercept and slope. This one is interesting because it doesn't have much going on. So let me show you what that looks like. That would be y is greater than or equal to negative 8. Y is greater than or equal to negative 8. So not a lot of math to do. We can pretend that this is y is equal to negative 8. And I hope that you remember that if y is equal to negative 8, let's actually use a scale of 2, 4, 6, 8. So let's say this is negative 8. If y is equal to negative 8, then I have a line that's going to go horizontal. And in this case, we have or equal to. So let's make a nice straight line going through here for our boundary. And then we need to color either up or down. If y is greater than negative 8, then we know we're going to be coloring up here. And this is actually pretty simple. All right. Okay, in conclusion, we are going to rearrange our equation into y equals mx plus b. We are going to graph the boundary. Okay, once the boundary, remember we need to know whether it is going to be dotted or solid. Okay, then we use a test point to determine which way we're going to color, on which side of the line, and then we're going to do the coloring. So that's all there is to it. Go to the ALEKS problems, see how you do with the practice.